Relations and functions notes. Virginia SOL A.7. The students will investigate and analyze functions, linear and quadratic families, and their characteristics both algebraically and graphically, including determining whether a relation is a function, domain and range, finding the values of a function for elements in its domain, and making connections between and among multiple representations of functions, including concrete, verbal, numeric, graphic, and algebraic. Again, you may pause to write notes as we go. A relation can be represented by a set of ordered pairs of numbers or paired data values. So 1, 1, 2, 1, 3, 2, 4, 3, and 5, 5 is a relation. They've been paired together, so that same information is presented in a table. A function is a special relation in which each different input value is paired with exactly one output value, a unique output for each input. So here are two examples of functions and non-functions. In the first table, we have xy, 1, 1, 2, 2, 3, 4, 4, 8, 5, 16. In the second one, we have 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. Note, the input in each x is 1, which resulted in 5 different outputs of 5, 6, 7, 8, 9. There should only be one output number when x is 1. So this one here is not a function, and it's the ones that causes the problem. Too many ones. This one over here has all different, so we're okay. This is okay. Here's some new terminology that we haven't discussed yet. In an ordered pair, the first number is termed the abacus. The abiscus. The x-coordinate, and the second number is the ordinate, or y-coordinate. The set of input values form the domain, and the set of output values form the range of the function. Input is another name for the x value, and output is another name for the y value. Abscissa. Patterns may be represented as relations and or functions. Here's 4 examples of different patterns. 1, 1, 2, 3, 5, 3, 5, 7, 9, 11, 1, 2, 4, 8, 16, and 1, 4, 9, 16, 25. Each one has a different term. So we'll call this one n's. These are all f of n's. So those 1 through 5 is the n, and the f of n's are there. The results. Each one's been placed in its own table. So we're going to try to figure out how to write the function rule. This first one it has a pattern. It's plus 0, plus 1, plus 2, plus 3. The next one would be plus, that's not right. It's plus 1, plus 1, plus 2. The next one should be plus 3, which is 8. Next one's plus 5, which is 13. This one doesn't have a really good function rule. It's a recursion sequence, so we would have to, the next one's going to be plus 8, which is 21. This is the Fibonacci sequence. Each one is determined by its previous term. You add the previous term to it. This one here has a pattern. It's a plus 2 pattern. So we would just keep adding plus 2's. This one does have a function. It's f of n equals, since it was plus 2, it's 2n. And 2n gives us 2, 4, 6, 8, 10, 12. So it's off by 1. So we would have to add 1 more to it to make sure it works. So if we tested this, 2 times 4, let's say, plus 1 is 9. So that one works there. This one is doubling, so the next one would be 32, then 64. From the doubling thing, you see it's times 2, times 2, times 2, and so forth. So if we try, so this function looks something like this. F of n equals 2 to the power of x. But this one doesn't quite work with just that one. 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. So it's off by 1, so we need it to show that. So we would subtract 1 from here. Now it's going to work. 2 to the 2 minus 1 is 2 to the first, which is 2. So now it works. So this is our function here. And the last one is showing a power here. So this one's not too bad. This one here would be 6 squared is 36, and this is 49. So again, the f of n in this case would equal n squared, every n squared. The last thing that we should be able to do in this unit is you should be able to connect multiple representations from a pattern in a concrete model. So if you look at this pattern, we have a 1 here. We have 1, then it goes 2, then 4, then 8. So you see what's happening. It's doubling, so it should go 16, then 32. So here's how you have to connect a concrete model like this to the other 4 types. There's word problems. So here was my example that I matched up with this. I said start out with 1 cell. On the second day, the cell divides into 2 cells. Then on the third day, those 2 cells divide into 4 cells. This continues on and on. The function rule would, or rule here, would be the independent is our days, which would be our x. And so our dependent is the number of cells, f of x. So we should be able to write a function from that if it works out. So I should be able to match that picture with the function rule, and the word problem matches. And then we would match it up in a table. So picture 1. So this is like our picture here, or these would be our days also. So there's the picture number or the day number, and then these will be our cells. So those are the number of cells on those days. And then of course you should be able to graph this on a coordinate grid. So I counted by 2's on this side, so everything's counting by 2's, and this one's counting by 1's on the x-axis. So each tick mark here is 1, 2, 3, 4, 5, which is my days. Then I'm counting by 2 here. So the first one was 1, 1, 2, 2, 3, 4. This would be 3, 4 here. This one here is 4, 8. And this one here is 5, 16. So again, the different representations on each one is matching each. So whether I could give you any of these, I could give you the graph first and you have to find the table that matches it, or I might give you the rule and then you have to make a table or use the rule to graph functions, or you have to use the rule or the table to write a word problem. Or you could also try to match it up with the concrete from the beginning. So all 5 of these representations throughout this unit, you should be able to translate from one to the other and be able to match it appropriately. And the math joke for today. Last night I dreamed that I was weightless. I was like, OMG, or 0 milligrams. Haha, that's a science reference there.